in the earlier video, what we done was we went ahead and calculated the or estimated the confidence interval. We estimated the confidence interval to different levels. So this is 68.3% or say 90% or say 95%, the usual confidence intervals. We went ahead and calculated that, but in this particular example, we had gone and done this after the standard deviation of the population was given to us. Now, if the standard deviation of the population is given to us, then obviously the standard deviation of the population has been calculated from the population mean. Otherwise, there is no way that we can go ahead and calculate the standard deviation of the population. And if that standard mean is already known, then also you would require knowing the various observations within the population to go ahead and calculate the standard deviation. So that is usually not practical, and the reason why it is mentioned in most statistics books and in various places is because we can understand the concept of estimating the confidence interval, and also because using the Z scale, using the Z values, it can only be done in this particular manner. So presume we do not have the Z scale, presume we do not have information of the population parameters. We are not aware as to what the population mean is or what the population standard deviation is. So mean any which ways is not mentioned over here, which is just okay, but not necessarily, So you obviously can't calculate the standard deviation without the population parameters, these two. So presume that this is also not there, the standard deviation is not there. Then most of the logic within this will not work. But still, let me just go through this once before I take you to the example wherein we do not look at any population parameters, and using the sample statistic, we go ahead and actually are able to predict whether the population mean would lie between a certain range, and go ahead and provide a confidence interval for that. Now let's look at what happened over here, just as a quick recap. We had the standard error of the mean, which is sigma bar calculated, which is okay, can be done because we have the sample size and we have standard deviation of the population. But presume we do not have this, then you obviously can't calculate the standard error of the mean sigma bar. That won't be possible. Once you input a certain percentage and you say this is the confidence level that I want to achieve, and you want to then find the confidence interval for that, the rest of it gets almost done automatically within this particular Excel sheet. So norm inverse we use, so that I've already explained in my earlier videos as to why we are doing that, and we get the lower Z value and the upper Z value, and from that obviously going ahead and using this particular formula, we get the X bar values, the lower X bar and the upper X bar value. What we can further do is we can understand that the lower X bar value is how many standard deviations away from the sample mean X bar. So that can again be done with a simple formula wherein you factor in the standard error of the mean, and you can also similarly look at the upper X bar value and as to how many standard deviations away is the upper X bar value. That can be done, and you can also see that whether this particular mean, which is the population mean over here, which I have actually gone ahead and knocked off in this particular example, is it coming within the range which is mentioned over here, yes or no? So the as many times as you get yes over here, you can then go ahead and say that 95% of the samples that we've seen, this comes out as yes, and because of which we have a 95% confidence interval for we have a 95% confidence level for this particular confidence interval, which is the lower X bar value and the upper X bar value. So what you're basically saying is that 95% of the times that you take samples from this particular population, and those samples are of say sample size n, and obviously the sample mean, which is the X bar, which is over here 217, will vary. So as many times, the 95% times it will fall within this range. Okay, having said this, let's look at another scenario. here I am taking some inputs. I am saying this is the time in seconds for certain processing that is happening within an organization. It can be absolutely any process for which we've gone ahead and noted these times, and we say, okay, so this is our mean. This is our mean for this particular process in seconds again. So this is the X bar, the sample mean, and we go ahead and plot the X bar in column C. The next, because we want to get the variance of this particular sample, and we also want to get the standard deviation of this particular sample. So the variance, that is S square, and the sample standard deviation, which is S. These two we want to deduce. That's the reason we're going ahead and doing these calculations over here in this table. So we go ahead and do X minus X bar. We square this X minus X bar and we take a sum. So in the summation notation, the way the formula is written is summation, that symbol for summation, on top n, down below I is equal to 1, then this X minus X bar in bracket, and the exponential notation 2, which means this is squared. And then the denominator of this particular formula, that is the sample variance S square, the denominator has n minus 1 as the denominator. The reason we take n minus 1 is because of the sampling distribution, and it is simple to understand. Presume you had around 10. Over here I have 22 as a sample size. Presume, as a simple just a manner of understanding, you had 10 of these over here. And if you were to go ahead and calculate the standard deviation and the sample variance, within that, I'm forgetting the term. One second. That is the degree of freedom. Yeah, the degree of freedom, which is mentioned over here. The degree of freedom will be n minus 1, because leaving aside one particular, say out of this, you could pick up any one of these. Out of these 10 observations that I've chosen, let's pick up 863, or let's pick up 903 or 957, whichever one, or 1745, whichever one. One of these observations cannot vary. Why it cannot vary? Because that is basically contributing to the calculation of the X bar. And if that one varies, then the X bar would vary. So that's why we say that the degree of freedom is n minus 1. So whatever is the sample size, minus 1 observations. So presume the sample size was 10. Or let's again take a situation wherein the actual situation where the sample size is 22. This actual sample size is 22. So all of the observations can vary barring 1. That's the reason we call it degrees of freedom n minus 1. Okay, so having calculated all of this, having calculated the sample variance, which is S square, which comes out to be the sum of X minus X bar exponential notation 2, which is the square of X minus X bar, divided by the degrees of freedom n minus 1. So I have not gone ahead and done degrees of freedom directly over here in the formula. Let me do that. Okay. One second. Let me check if the formula is correct. I don't know what I had done earlier. I had gone ahead and done 22 minus 1, but that is not coming out to be the same. Why? Yeah, sorry, the bracket was missing. Okay, so one and the same thing. Fine. So sample variance S square comes out to be this particular figure over here. And the standard deviation is of course the square root of this particular figure. And the sample mean X bar we've already calculated, that is 1489.41, and the sample size is n. We've gone ahead and counted our sample size. the confidence level that we want, or the cumulative probability percentage that we want, is 95% over here. And like it says on top, we are estimating confidence interval of the population mean without population parameters. So you will see that there is no population parameter mentioned over here. So we don't necessarily know what are the population parameters. We don't know the population mean. We don't know the standard deviation of the population. But from a sample, and that is also one sample only of size 22, we are going to estimate the confidence interval of the population mean. So the standard error we've gone ahead and calculated. Sigma bar, the degrees of freedom I have already explained, that's n-1. Now the t value. Now this is something which is slightly different from the z scale. So from the z value, it is slightly different in the sense that the t distribution has more variance in it. So on the edges of the distribution, or on the tails of the distribution, there are more values than there are values around the mean of the distribution. So that is one basic difference that we need to understand. And thus we've gone ahead and calculated the t value. There's a separate formula for this, then the z value. And then we go ahead and calculate the interval half width. And we get the interval lower limit and the interval upper limit. So that is how simple it can be once we introduce the t value. And because we've introduced the t value, we do not anymore need any population parameters to estimate the confidence interval of the population mean. We don't need any population parameters. We can go ahead and get it done by using the sample statistic. Also, as seen in the earlier example, this very clearly states that the lower x bar value, which is the interval lower limit over here, is 2.07 standard deviations from the sample mean, which is the x bar, and again the upper is again the same standard deviations. Now we can play around with this and have a look. What will 90% look like? Less number of standard deviations, 1.72, and the lower limit. Okay, let me just do a quick that'll take too much time. So let me just look at, say, 99%. So that is what 2.83 standard deviations, and 95 is 2.08 standard deviations. Okay, and let's look at 99.9999. Let's see, that's 6.80 standard deviations. Okay, and it's showing 100% over there because it's okay, the cell is formatted in that manner. Let me actually go and put 100 over here and see what happens. Wow, great. Okay, perfect.